Thank you, Davide. Thank you to all the organizers for this nice session. It's always very nice to be back in Pisa. Yeah, today, a bit differently from what we saw so far. I mostly work with stochastic partial differential equations and then studying straight away their ergodic properties and their response theory. So on a previous work of mine with Giulia Carigi and Tobias Kuna, we analyzed the response theory for generic stochastic partial differential equations, and one of the fundamental ingredients to do this is to ensure that your system has a spectral gap or some exponential ergodicity. So this work here focuses on precisely establishing the ergodicity for a model, an energy balance model for global temperature that was originated in 1969. That is the same year in which this picture has been taken, actually, from, I think, Apollo 11 mission. And of course, yeah, sorry, just to acknowledge my collaborators, this is done in collaboration with Jochen Brocke, Marco Renata, Tobias Kuna, and Christina Blank. So, as I just said, this work focuses on what does it want to investigate, the long time average behavior of the solution for a model for the zonal, so latitudinal average global temperature, and this is one of the first steps to go then and investigate also the response of this type of models with different type of forcings, and we're going to do it with mathematical tools like the exponential, establishing exponential DCP. And we're going to look at the model with some noise. So probably this audience doesn't need this little introduction, but so the energy balance model are actually a hierarchy of models. So there are several depending on what are the features that you want to capture of your model. It could go from just zero dimension, which you just look at the temperature of the mean of the Earth, so the entire thing, or maybe you want to take into account that you have different temperature depending on your latitude. We know very well how that is different from the pole into the equator. And then depending on how much you want, you can go up to 3D, and so you're looking at general circulation model, etc. So different models for different questions, as we have learned in these years. In particular, the EBM models, like in 1D, for example, from 0D and 1D, have a long history, starting from 1969. And after the work of Michael in 1976, there have been even more studies in also mathematical framework, but I find that like a rigorous mathematical analysis of this type of models has been like moving a bit more in the last years, I would say. So just some references if you're interested in the topic and you're not from the topic, otherwise you know them already. Okay, so how does this model look like? I'm not looking just at a one layer model, but at a generalization of this model that was suggested by Valerio Lucarini and then was investigated further in this nice paper of 2 years ago. So in this system, what we're looking at is the temperature at the atmosphere and the surface. We're looking at the entire sphere, but we're effectively just looking at the zonally average. So, like as I said, with the different latitudes, and we could think of flattening this out to become just the domain, a straight line. It goes from -1 into 1, where -1 is the South Pole and +1 is the North Pole. So you can imagine that you have all this temperature. But on this, we're adding extra complexity with these two equations, one for the atmosphere and one for the surface, as I just said. So on the left-hand side, we would have some, of course, how it changed in time and some diffusivity. What do we have here is a very particular type of degenerate, in a sense, operator, because you can see that on the poles, it would just behave very badly. But this is to account, of course, for this simplification that we just did of the entire sphere into one line. And so this will need a little bit more care, but it's not too bad, actually. It's going to be our friend again. And on the right-hand side, went the opposite direction. Here you go. On the right-hand side, you would have all the forcings, all the interactions that you can expect from something like this. So on the right-hand side, we have, for example, some linear terms that would have to describe the interaction between these two layers that I'm introducing. And of course, there are several mechanisms behind this interaction. We would like to also see some the action of the geophysical fluids are actually carrying this temperature, and this is a simplification model in which we just put it down as a linear part here when you have the difference of the temperatures. And the nonlinear part instead is what you would expect from this type of models that look at the temperature for the entire globe, so that you have some infrared radiation emitted from one layer to the other and absorbed, and so this accounts for these different signs and factors that are appearing in front of these terms. So these terms are, of course, like a fourth power, like in the Boltzmann law. And this is our, for mathematical terms, our nonlinearity that is pretty nasty because it's a fourth order, and so there are not many nice properties as, for example, there could be in a more advective type of nonlinearity. And these terms here will be the one that would also have inside the feedback of the albedo. So it would be interesting to look at something where these guys are changing with the time, but this is beyond the scope of this work, where we're considering something that is autonomous, so the forcings are not depending on time in this case. Any questions so far? I guess we're having a short time for questions after. Okay, let me just go back. So in the mathematical framework, what we do with a PDE like this, we go and study them in some functional spaces when we try to find the solutions for these things. And so we have to find what is the right setup to solve the solutions. Of course, sometimes the higher you make the setup, like the more general you go, sometimes it's easier to find solutions on your problems. One simple example that's been said sometimes is that if you take your dynamic higher enough, you end up with a linear dynamic. Now, when you do the Koopman operator, that is the trick that a lot of people like, that you end up with a linear operator, but you're working with both spaces. Yeah. Okay, so this is not the case. We're not going to end up with a linear thing, even if we make it very easy, but or if we make it very high up. But the natural setup to look at this is going to be some sort of weighted sublet, because we have just to account. I'm not going to go into the details, but just point you to what is the critical points here. Is we have to account for the non-degeneracy that we saw in this diffusion. Usually the diffusion is the Laplacian. This is a modification of the Laplacian. It's still our friend, but we have to make sure that it's our friend still. Okay, so the space where we're looking at is something that would have to take into account this part. The nice thing of this space is, despite that, this is going to be always compactly embedded into LP for every P, not infinity, but this is crucial when you want to study the existence of invariant measures for these systems, or study its attractor. These are very important features from a mathematical perspective. And so I mentioned a lot about our diffusivity here. Usually, if you're familiar with fluid equation, you usually have the Laplacian that is your helper, and you denote it with A when you go higher up in the hierarchy of spaces. And what I mean with the dissipation is still good is that it retains the same properties that you would like from a Laplacian, that you have maybe a sequence of eigenvalues that is growing and their eigenfunctions, so like the Fourier space, for example. No? But you can do a similar thing to what would you do with the Fourier series from eigenvalues of the Laplacian, but from something like this. And you would, in a sense, expect this to also happen, because we have it for the Laplacian on the sphere, and this is an approximation of looking at an equation of the sphere to the line. So anyway, so this is good. It's still our friend, especially for this type of analysis. Then to study ergodicity, we add some noise. There are several ways in which we could add noise, and I'm happy to discuss this later. The first thing to do is, of course, to add an additive noise in this context, and we can consider it like acting on enough degrees of freedom. So this is a first instance of trying going always the opposite direction. You go. So after we do all this, the results are what? First of all, well-posedness. It means that we have a unique solutions for this system. So good. Like we did a good job in like selecting this as a model, because if we don't even have a solution, that is this even a good model for what we're looking at? So we do have at least unique solutions, and it's also depending continuously on its initial condition. There's some particularity with the spaces that we had to look at that depends on the nonlinearity that we have in this context. But what I want to discuss in this...
Sorry, but what is P? What is the probability P?
The probability P is the probability underlying for the Wiener process that I added. So I have added...
So it doesn't have anything to do with the invariant measure of the system?
Not yet. Not yet. This is the probability that comes from the noise. Thanks for the question. So if we have at least this nice property of having continuously dependence on T0, and we have uniqueness of solutions, we can start thinking about ergodic properties of this system, meaning that we could try to associate some semi-group, etc. Okay, before giving you the statement here, let me remind what are the notations that we are having and here.
Yes, the continuous dependence on the parameter is also proven?
No, it's not. And depend, what parameters?
For the problem?
No, like the epsilon or the lambda or anything like this. For the part of like just the solution, I think that could be done, honestly. For the response, that's a different business. But yeah, we can check that. I think usually it's not too much problem.
Typically, for B is an important property. The continuous dependence on the parameter is the problem.
Yeah, because otherwise, if on simple ODEs you would see the transition, not the critical transitions. That's what you imagine. So yeah, let me just write up these things together. So what I mean here with the transitions probabilities are just the laws of my solution. So what is the probability that if I start at T0 at time T, I will end up in this set here. Then if I take expectations with respect to this probability distribution, I end up with the Markov semigroup that I think has been, in some contexts, we call Koopman operator, these kind of things. But and then an invariant measure is something that's a way to measure observables or any other thing that you might be interested in that is not affected by the dynamic, because if I act on the dynamic first, then it doesn't see the presence of the dynamic. So these are the objects that we're looking at. And in the context of Markovianity, like here, if an invariant measure is unique, it's also ergodic. And the nice thing of ergodicity are here is that you will then be able to represent temporal averages of some observable that you're interested in into, let me say, spatial averages, even if this, of course, is averages with respect to the invariant measure, and these are highly non-trivial type of distributions on this state spaces. Okay, so we don't have a clear representation, like numerical, of this invariant measure. And even better, like if we could have even better convergence, in a sense, you can see that this is some sort of convergence of this these laws, no, the Markov semigroup that I told you before into measure, no, maybe we can have something even better. This is a distance, fast time distance between them. That this is actually exponentially converging in time and not just on average in time. So this type of result is the one that we're looking for, and there are several techniques to try to do something like this. Yeah, so if that is what we're looking at, effectively what we're proving is that you have a sort of contraction of this loss. So if you start from 2 points further away, then the laws of your solutions are going to get closer and closer in appropriate distance, is what's happening here. And so in a sense, you're losing track of your initial condition. And so in a sense, you can look at time series of this, and like it makes sense because you don't have to keep track of your initial condition. This is why you want to do something like this. Okay. How are we on time? My turn. Okay. We're good.
Still have 1 minute before I...
Oh, okay. So I give you like 3 minutes or something too. Okay, so I think in the abstract I promised you that we'll look at this with the Harris theorem, with the weak Harris theorem, but I thought it's a bit too heavy to see the actual proof of the Harris theorem. But if you're familiar with Markov chains, that is usually one technique that is used to establish exponential ergodicity. So not just the convergence, but convergence with a rate, and the rate being exponential. And in that context, in the Harris theorem, what you want to do, you want to control how far away your solutions can get from each other, and the weak Harris theorem is helping you to do that very hand-wavingly. Now, for PDEs, so for SPDEs, there are some of these conditions that are usually not satisfied because of the context of this. When you're looking at PDEs, you're basically looking at infinite dimensional systems because you're working on functional spaces. And so some of these techniques do not apply. In 2009, 2011, this theorem that is fundamental for exponential ergodicity has been generalized to work also on infinite dimensional systems, meaning to work also for stochastic PDEs. And this was the work of Heider, Mattingly, and Schweitzer. I think it's there, yes, on the bottom. Okay, but this requires to find some very fine, let me go back here, some very fine distances to work with. Like what is complicated is to go and construct distances from which you can prove things. And more recently, in this paper here, they provided a very neat toolbox of like things to be proven so that you can, in the end, construct the distance that give you that contraction, and then from the contraction you have the rest. So the idea behind this is not to look at just two solutions with two different initial conditions. Remember, we were looking at the laws of the two different initial conditions that we want them to get closer. But maybe one of the two, we add a control, we add a nudging, we add an extra term that is helping me move these solutions to the other one. And this is the role of this guy. So I'm feeding back inside the equation the error that I'm making between this equation and this equation. So that when time goes to infinity, I hope that these two guys are getting closer and closer to each other. That's the idea of adding a nudging. It's been used in a lot of framework, from data simulation to control, and it's very useful. And this idea was already appearing in almost more than 20 years ago in these works of Heider, for this type of works at least. Okay, so if we have these two guys, like this is a parameter that I can tune, and I hope that I can make it very large, so it's helping me bring these two solutions together. Then imagine I have like some sort of triangular inequality for this guy. I will plug in the middle just this guy. So I will have the original one, the one with the nudging, and then from this other part, the one with the nudging. Apologies here, I have Z, but it should be T. And then these guys that would have the same initial conditions, but what is different now is going to be the noise, because I've added this part. So over here, this part is taking care of whatever is the difference, not in the initial conditions, but in the noise that I'm having on my equations. And this can be done with knowing how the noise acts, and with Gersam theorem that allows you to do equivalence of measures. While this other part, it's a bit more tricky because you have different initial conditions, and this is where this guy needs to help you. And if you're interested about these things, I find this paper very good overview of the idea, at least, of the asymptotic coupling. Then for our case, how does it look like? If you take then the difference between the two equations, you end up with something like this. In F, I chucked in all the nonlinearities that I had, all the stuff that was on the right-hand side, and here I have the diffusivity that I discussed a lot about, but I told you it's still nice diffusivity, and then I have this guy. Then what is the first thing you do? So I do a L2 scalar product. You multiply with the thing itself and you integrate. It's the first trick in the toolbox that you have. And after long estimating and long work, you end up with an expression of this type, or whatever. So nice, here I have the difference between initial conditions, and so this, when these guys get closer, this guy gets closer, or anyway, I can control this with the difference between the initial condition. But here on the right-hand side, I would have I want something that goes down in time, or that I can control with the time. And these guys gets in the way. This guy is not particularly harmful because of the well-posedness that I showed you before, so I know how to control that guy. But this guy here is the nudged one, is the one with the control. So the one with the control would have inside, again, this parameter, the mu, because I've added that guy. So I have to be very careful when I do estimate for this guy that I don't end up with like mu to the square or mu to the fourth, something that would kill any gain that I have over here. Because mu is a parameter that I can choose, and I want to make it very large so that this guy stays negative. So a lot of effort went into reaching something like this, and then estimating this in correct way, but this was a successful work at the end of the day. Okay, where to go from here? There are several questions. Of course, one was already made, like, do we know then anything better about the response theory when we have this this result? And especially the parameters that would be interesting to look at are the lambda, the q, but I think most importantly the epsilon, that is the absorptivity of your atmosphere. This techniques, of course, is very mathematical heavy, and the distance I mentioned, it's a bit complicated to actually compute, and it would be very nice to have a result with a simpler distance, but to the best of my knowledge, I don't know how to do this at the moment. And to have a quantitative estimate on the mixing rate. This would be very interesting to know, to more properties of the model itself. But the Harris theorem is not very good in giving you a mixing rate, so how fast is actually this convergence, apart from being exponential. Then we have, of course, this is more relevant for climate change, like if we have forcings that are time dependent. And I've hinted at this when I introduced my noise. What is the better noise to add? Like, what is that the physical one that we want? Do we want maybe a noise that is instead like very, very rough? Or do we want to add also some sort of advection and add the noise inside the advection? This is a direction that I'm also up for suggestions for people that are more expert than me in the practical use of this type sort of models. Finally, like, one part that is also very interesting is like coupling then this model that's just for the temperature with the dynamic models. So with dynamics, with models that, for example, like the primitive equation or the quasi-geostrophic equation, so that you have an interaction between the temperature and the dynamic itself. And we're starting going in this direction with the PhD of Federico Parnassaro that is sitting here in the room. So if you want to know more about the Mao model, I think some of you know, like how to actually study it from a mathematical perspective, you can ask the expert in the room. And that's it, some references and Bloomington on the back. Thank you.
I think that we are a bit behind schedule, but we can take one quick question. Yes?
Sorry, I didn't understand the role of the environment measure and if you prove the existence of
Yeah, we did. Sorry, I didn't present it, but we did show also the existence. It's just that usually the existence is a bit easier to show, and it comes from just having nice a priori bounds or like energy.
Okay, but do you know anything about like is an environment measure which is absolutely continuous? Or
no. You cannot. Absolutely continuous with respect to what? We don't have the bag here.
But it's a unique environment measure. We do know this.
Okay.
But from the additional result that
I mean, okay, you don't have the bag, but maybe it's a sort of physical measure. I mean, something that you can observe. Otherwise, you have ergodicity with respect to some measure that you don't know if they can observe, because maybe it's a distribution or some sort of delta.
Yeah, precise. I mean, that's the best thing you can get from a PDE, to the best of my knowledge, because this is going to be an environment measure that is supported on the attractor, and the attractor is a very rough thing over here.
Exactly. There's only one environment measure. We know that there's but, but more than what Giulia has presented, we don't know at this point.
Okay.
But in general,
But do you agree that if you don't know, I mean, of
course, it would be great to have more knowledge about the, you know.
Because you are mixing with respect to the variable measure, but you don't know what it looks like.
No, exactly. Yeah.
Okay, sorry.
Thank you.
And then another question, if you have, how difficult will be to understand non-stationary mimics like climate change?
Like something that is time dependent?
Yes, like, I don't know, Stefano over there, for
Yeah,
example, right?
because
Because this is what is interesting for us.
but it's, I don't know, the interpretability of looking at all these semi-groups.
Shifting.
Yeah.
But also, Giulia, the epsilon parameter, which mimic for you something like connected with the greenhouse effect.
Yes, exactly. I said that is one of the parameters that I would like to look at.
Okay, that
But,
can be interesting to have some bound.
Yeah, for sure.
Yeah.
At least at the level of response that we can make,
sure.
this is a sort of response to that. It's still not depending on time. Like,
Yeah,
maybe
yeah.
we would have a
Like
range.
fixed range,
Fixed range.
that already would be very nice. Yeah.
Okay, next year we'll
Next
come
year,
with that.
yeah.
Or in 2 years.
Yeah.
We'll come in 2 years.
Thank you very much for this very interesting talk.